in a world where ME 250 students are unsure of their tolerances. Comes forth a hero to help these lost students. He goes by the name of the Tolerant Superhero.
What can I help you with, student?
I need to put these pieces together, but I'm not sure how to get the right fit.
I can help with that. If you're going to mass produce a product, you will use the ANSI standard fit types and classes. To start, you will first need a running or sliding clearance fit. This ranges from RC9, the loosest, to RC1, the tightest. There are locational fits too. They help you determine the location of the mating parts. Locational clearance fit is when the maximum limit of the shaft is less than the minimum limit of the bore diameter. Locational interference fit guarantees the shaft and bore will interfere at every point within their tolerance zone. To achieve this, you may need to use excessive force or change in temperature to expand the hole. Lastly, the locational transition fit is used when a shaft must be held in a precise location. You should also be aware of force fits. This will provide a constant bore pressure throughout the range of sizes from FN1, the loosest, to FN5, the tightest.
That all sounds great, but I might need a little more help in understanding it.
No problem. Let me give you an example problem and see if it makes more sense after that. In this exercise, we are given a basic size of 0.35 inches in a fit of RC7. You can see in the diagram below what this looks like. As shown in the table, the red highlighted region shows the fit and the blue highlighted region shows the basic size. Where the highlighted column and row overlap is the class with which we have to operate in. The tolerance values are listed in thousandths of an inch. For example, the standard limits of the hole would be 1.4 thousandths as the upper limit with no tolerance on the lower limit to avoid completely blocking out the shaft. The shaft's tolerance fit, on the other hand, can only be smaller as the upper limit is negative 1.6 thousandths of an inch and negative 2.5 thousandths of an inch as the lower limit. This graph shows how we can decide our tolerance fit based on the class and the size of the shaft.
That makes sense. I will start my project right now.
Whoa, hold up. Are you mass producing this product?
Well, no. Why does that matter?
Well, there's a special set of simplified rules for parts that are not being mass produced. They are called the ASA recommended allowances. To better explain the chart, I will show you the definitions of the 4 kinds of fit. This is the fit chart of this simplified system. You can use this chart to find the standard fit you need. Note that you need to measure the shaft with a micrometer before you ream the hole.
So the first type of fit is called the running fit, which is for assemblies where one part will run in another under load with lubrication. The second type is called push fit, which ranges from closest fit that can be assembled by hand through zero clearance fit to very slight interference fits, assembly selective and not interchangeable. The third type is called drive fit. This fit is to be used when parts are to be tightly assembled and not normally disassembled. It is an interference fit and requires light pressure. The fourth and last type of fit is called force and shrink fit. This fit requires heavy force for cold assembly or heat to assemble parts as a shrink fit. It is used when the metal can be highly stressed without exceeding its elastic limit. Wow, okay, that's a lot of information. You think you could give me an example for the ASA allowances too, to help me better understand?
Yes, of course.
In case you don't understand what is going on, I will show you an example problem for certain fits. Given 0.751/0.752 pin, and we would need a running fit for severe loads. If the total hole tolerance is 0.003, find the limits of the hole. First, you'll have to look for the allowance in the table, which is 0.0015. Because the smallest hole is the largest hole plus the allowance, the smallest hole will be equal to 0.752 plus 0.0015, so that would lead to 0.7535. The largest hole, on the other hand, would be equal to the smallest hole plus the total hole tolerance. So that would be 0.751 plus 0.003. So that would total to 0.754. So the limits of the hole would be 0.754 and 0.7535, which all the dimensions are in inches. Thank you. This has been so helpful.
Don't worry, my young Padawan.
I will strive to become like you in the process of tolerances and precision and the execution of my result. Now, I will be able to successfully machine single parts to the ASA standards or whole assembly lines to the ANSI standards.
No problem. If there's anything else I can do, please let me know.